Hi, this is John Whitaker for the Probability 1 class, and today we're going to have an extended lecture. This is our 25th video lecture, but it could quite possibly be our 25th and 26th lectures put together. So we're going to go for some time in that there's no good breaking point, if you will, for the material. What we're talking about is about random graphs and conditional probability. And we're going to be asking a question about the probability of the connectedness of a random graph. But first, we need to say what is a graph and talk about aspects of it, and what is a random graph. Okay, so we'll start off today with the definition. It says a graph consists of a set V of elements called nodes, and the set A of pairs of elements of V called arcs. So when we think of the arcs, those are lines that connect the pairs of elements that constitute an arc. And so pictorially, we represent graphs by drawing circles to represent nodes, and drawing lines between nodes I and J when IJ is an arc. So it's a member of A. So we'll do an example. If we let V be the nodes 1, 2, 3, 4, and 5, and A be the set of arcs, and they look like 1, 3, 2, 3, 1, 5, 2, 4, and 1, 1. Okay. Then this is what we could have pictorially. We have maybe 1, here's 2, here's 3, here's 4, and here's 5. Okay, and so those are our nodes, and 1's connected to 3, 2's connected to 3, 1's connected to 5, 2's connected to 4, and 1 is connected to 1. So that's what my graph looks like. And this yields, especially this loop here, this arc, yields a definition. The arc II is called a self-arc or self-loop. Okay, next we want to look at the definition. It says in a graph, we say there exists a path between node I and node J, where I is different from J, if there exists a sequence of nodes I sub 1, I sub 2, all the way up to I sub k, and then j, such that we have I to I1, I1 to I2, all the way up to I sub k minus 1, up to I sub k is a pairing, and then I sub k up to j is a pairing. Okay. These are all arcs, okay, in the graph. Okay, next we're going to talk about what it means to be connected. So, as a definition, if there exists, or there is, a path between each of the n choose 2 distinct pair of nodes, we say that the graph is connected. So here, it's a picture. If I have, as an example, this graph, 1, 2, 3, 4, this is a connected graph. And the reason that it's connected is from any 2 nodes, I can get there through a path. So from 2 to 3, I can get there from going from 2 to 1 and then 1 to 3 along that arc. And so that's true for any pairs of nodes that we have here. Another example, so that's is a connected graph. If I had 1, 2, those were connected, and 3 and 4, those had arc between them. Well, this particular graph is not connected. A connected graph. Okay, it's not a connected graph. We call it disconnected. So we're going through terminology here about graphs, and we're about to get to a random graph, which is what we're going to talk about probabilistically. Okay, so it's a definition. A random graph is a graph with nodes v equal 1, 2, 3, all the way up to n, finite many of them, and arcs A equal to the set of I, x of I running from 1 to n, where x of I thought of as independent random variable such that the probability that x of I is equal to some j is equal to 1 over n, where j is some node 1, 2, all the way up to n. Okay. Okay. What we're going to be interested in computing the probability that a random graph is connected. Okay, I'd like to say something about random graphs that are different than graph in general. So here, first of all, in forming a random graph, from each node, each one of them, we select at random one of the n nodes including I itself, including possibly I itself, and join I with the selected node by an arc. Okay. What this means that can be different from just a graph in general, that in a random graph, each node only has one, if you will, arc coming out of it. Now, it can have some other arcs coming into it, but just one is coming out of it is what we think of. Okay? Let's look at some examples. This is A. So if I have 1, 2, 3, 4 nodes, and we would say 1 is going to 2, if you will, and for 2 we go to 3, and for 3 we go to 1. I'm not putting arrows on here, but that's what's happening in this particular example. And then 4 goes to 3. Okay? This is a random graph. That is connected. B. If I have 1, 2, 3, and 4 as the nodes again, and let's say 1 goes to 2, 2 goes to 3, and 4 goes to itself, this is not a random graph. The way we have them defined, random graphs will have n arcs. And so here there are 4 nodes, but we've only got 3 arcs. Do 2 more examples. Okay. By the way, before I move on, this graph is not connected. Okay? It's disconnected. Another example, if we have 1, 2, 3, 4, and 1 goes to 2, 2 goes to 1, 2 goes to 3, and 3, 1 goes to 2, 2 goes to 1, 3 goes to 2, and 4 goes to 3. Think of it this way. This is a random graph that is connected. And then a final example. We have 1, 2, 3, 4. We have 1 goes to 2, 2 goes to 1, 3 goes to 2, and then 4 goes to itself. This is a random graph. That is not connected. All right. Now, with that background, we'll turn to the question at hand about the graph, the chances that the graph is connected, random graph is determine if a random graph with n nodes is connected we will look at the following construction. Okay. So here's what we'll do. Starting with some node, let's say I sub naught. Okay. We note the sequence of nodes I naught, x of I naught, so tell what it has a arc to, x squared I naught, which tells you what x of I naught, which is a new node, or which is a node, gets sent to, and so forth. Where we'll say x superscript n of I naught is equal to x acting on x of n minus 1 acting on I naught. Okay, so we're going to define a random variable based on this type of sequence of nodes. We're going to let n be defined to be the first k such that x of k of I naught is not a new node. Okay. For example, in our example A, where we had 1 was associated to 2, and 2 was associated to 3, and 3 was associated to 1, and then 4 was associated to 3. If we let I naught be equal to the first node, then x of I naught, or x of I naught, so that's equal to x of 1, and x of 1 was 2. X squared of 1 would be equal to x of 2, which would be equal to 3. And then x sub 3, or x superscript 3, I should say, of 1 is x acting on x squared, which is of 1, which is x acting on 3, and x acting on 3 is sent to 1. And so n here is equal to 3 in this example. Now, to obtain the probability that the graph is connected we condition on n that's what we do. So this is nothing more than the total law of probability, okay? So the probability, the random graph, that's what we're talking about. It's a random graph. Probability that, I'll say graph is connected. That's going to be equal to the sum, as k runs from 1 to n, of p, the probability the graph is connected, given n equals to k times the probability that n equals to k. All right. Now we're going to be interested in this quantity, this conditional probability. And so let's start talking about it. Now, given n equal to k, the k nodes I sub naught, x of I sub naught, not x of, x of I sub naught, x squared I sub naught, all the way up to x sub k minus 1 of I sub naught. That can be thought of, well, as being connected. So that's a string of connectedness. Connected nodes. I'll say they are connected to each other and there are no other arcs coming out of these nodes to other nodes that are not in the sequence I naught, x of I naught, all the way up to x raised to k minus 1 of I naught. Okay? Now I will say this, there might be arcs coming in, but none going out to the nodes. Okay? we can consider these k connected nodes as a supernode. One entity kind of itself. And consider the graph as a graph. Of course, when I say graph, I think kind of somewhat of a random graph. That's a random graph. As a graph having one supernode and n minus k, what we call ordinary nodes. With arcs coming from each ordinary node what we'll note the probability that a particular ordinary node has an arc to a supernode, to the supernode, that's equal to, okay, so it would be k over n. That's right. Because there's k nodes there in the supernode. And the chance to go in for one of these ordinary nodes to go into any node was 1 over n. So, in order to progress towards a solution, we examine the following. Following lemma, which helps us in considering supernodes. And so, in terms of the probability of the connectedness of the random graph, what we're going to be thinking of here is that we're going to be thinking of the situation I'm about to describe, this lemma, is having to do with the probability of the connectedness given n equal to k. Okay. So here's the lemma. It says, given a random graph consisting of nodes 0, 1, 2, all the way up to R, and R arcs. Okay. It says there's a random graph, but here we have R plus 1 nodes, if you will. And when I said you have to have the same number of arcs as you have nodes, so in parentheses I'll say the other arc is the 0 goes to 0, that's self-loop. Okay. Okay. So that's a parenthetical expression. So we have these R arcs given by I, Y sub I, and here we'll say I is equal to 1, 2, all the way up to R. Okay. Where let me define Y sub I. Is equal to, it's J with probability 1 over R plus K, and J is equal to 1 up to K, up to R, not K. And here, it's equal to 0 with probability K over R plus K. And so this is true for any, we're defining this Y sub A for where we have any fixed natural number K. Then, the conclusion of the lemma is the probability the graph is connected is equal to K over R plus K. So the way that we prove this lemma is what's known as by, well, it's by something called strong induction. So it's by mathematical induction, but we have this word strong here. The reason we have this word strong is because what we say is that for induction, we say, hey, we have to prove this for the base case, and then we say, assuming it's true for R equal to N, we have to show that it's true for R equal to N plus 1. So we're doing this by induction on R. But by strong induction, what we're going to say is, and this is allowable, that we'll have to do it for the base case when R is equal to 1. But we'll say, well, let's assume it's true not only for R equal to N, but for R equal to N and any natural number below N. So suppose it's true for R less than or equal to N. That's allowed. So it's by strong induction on R. And then once we assume that the statement is true for all R is less than or equal to N, then we have to show the statement is true for r equal to n plus 1. Okay. Now, so let's start off. We let r be equal to 1. Then, for the random graph, to be connected. So with r equal to 1, we got two nodes, 0 and 1. So for the graph to be connected, we think of 0 having a self loop. That means that this node 1 has to be connected to the 0. So that means y of 0 has to be equal to, 1, y sub 1 has to be equal to 0. Okay, that's what we're looking at. So we're trying to compute the probability that that happens. Okay, now the probability that y sub 1 equals to 0 is equal to this k over 1 plus k, which is equal to k over r plus k, because r is equal to 1. So we say the statement is true. When r is equal to 1. Okay, for the strong induction, we assume the statement is true for all r less than or equal to some arbitrary but fixed n. We want to show the statement is true for r equal to n plus 1. So to compute that the graph, compute the probability. That the graph is connected in this situation, okay, in the r equal to n plus 1 case, we will condition, so that case, we will condition on the number of arcs for which y sub j equals to 0. So here's what we're thinking. The probability that the graph is connected add equal to the total all probability, sum as I runs from 0 to n plus 1, or n plus 1 non-zero nodes here. Probability of being connected, the graph being connected, given I of the y sub j's equal to 0, okay, times the probability that y sub j equals to 0. Okay, this is going to be equal to, I can say something about the probability that y sub j equals to 0. And I want to do that here. So this is the sum as I runs from 0 to n plus 1. Probability, this conditional probability of graph being connected, given I of the y sub j is equal to 0 times. Now, the probability that y sub j is equal to 0, okay? I didn't write that down correctly. I should have said the probability that I of the y sub j is equal to 0. Okay, so here's what we do. This becomes a binomial random variable. And so what this is that we have r plus 1 choose I. The chance of getting I sub j equal to 0, which was k over n plus 1 plus k. So that's going to be raised to the I. And then we have times the chance of this not happening, which would be n plus 1 over n plus 1 plus k, and that's supposed to be raised to the n, or here it is, I wrote down r, but really it should be n plus 1, because that's what r is. And here this should be n plus 1 minus I. Okay, so that's what we get. Okay, now what we're going to be interested in, let me write this down a little bit lower. So times the n plus 1 over n plus 1 plus k to the n plus 1 minus I. So that is. What we're going to be interested in is computing this. This conditional probability. To compute the probability, so probability of connected given I of the y sub j's equal to 0. Okay, we reason that that given exactly I of the arcs, remember that's the nodes that are in 1 through n plus 1, are going to zero, and the n plus 1 minus I remaining nodes do not have arcs. To the 0 node. We we can view, here's the situation. As having n plus 1 minus I ordinary nodes and we'll say a new and a new zero node, okay, consisting of the old node, old zero node, I should say, and the I nodes that have arcs to the old zero node, because that's what the new zero node consists of. Okay? And that kind of gets us back into the same case for which this lemma is describing, but where we have less number, if you will, of non-zero nodes than n plus 1 possible. Okay. Now, the probability that a particular one of these n plus 1 minus I nodes, say L, has an arc to the new zero node is, okay, so this is what I'll write down. It's the probability that the L node connected to new zero Okay, what that's equal to, it's the probability, it's a conditional probability, that the L node, I'll say goes, is connected, if you will, goes to one of the I nodes, okay, connected the old 0, given L does not connect to the old 0. And that's a conditional probability. So that's equal to the probability that the L node is connected, if you will, has an arc between it, to one of the I nodes connected, if you will, has a path, has an arc to the old I, to the old 0, I should say, and L does not connect to old 0. All that probability over the probability that the old the L node is not connected to 0. That's the same thing as the probability that L node is connected to an I node that is connected as an arc. You understand what I mean? To old 0 over the probability that the L node is connected, is not connected. Stay. To old 0. Okay, so here, this is equal to there were I nodes connected to the 0, so there's I ways that this can happen. N plus 1 plus K over, here we have 1 minus K over N plus 1 plus K. Just in that situation, which is equal to, that's based on the I sub j's for this situation. So it's I over N plus 1 plus K. I'm doing some of the algebra here. All over N plus 1 over N plus 1 plus K. That's the big fraction here. And that's equal to I over N plus 1, which can be thought of as I over N plus 1 minus I plus I. Now, the probability that the Lth node goes, again, just to specify what I mean by goes, as an arc to a non-new 0 node that's given by, I'll do it the same way we did before. That's equal. The question is the probability that the L node is connected or has arc, it means the same thing, to new, zero node. Okay. We'll do this as a conditional probability. That's equal to probability L has arc connected. I'll just say connected. To I'll just new zero. Given L node is not connected to old zero. Okay. This is equal to a probability of L connected to new zero and L node not connected to old zero all over the probability that the L node is not connected to old zero Okay. Okay, that's equal to the probability that the L node has arc connected to one of the n plus 1 minus I nodes not connected to zero, okay, over, what was the probability not connected to the old zero? It was 1 minus k over n plus 1 plus k. Situation. And that's equal to, so here it'd be 1 over n plus 1 plus k. That's what the top part is. Over n plus 1 over n plus 1 plus k, which equals to 1 over n plus 1, we could say minus I plus I. So with both of those probabilities being in existence, that puts us in the same situation as what the lemma is talking about. So, the new situation is exactly like the situation
of the lemma, hypothesis of the lemma, where we have n plus 1 minus I nodes, and k is equal to I. So as long as I is greater than or equal to 1 by strong induction, okay, the probability the new system is connected, new random graph is connected, is I over n plus 1. And that's equal to the probability that we have a connected graph given, okay, given what? I of the y sub j is equal to 0. That's what that is. Now, we do have to consider the case where I is equal to 0. If I is equal to 0, okay, then, excuse me, the probability connected given I of the y sub j is equal to 0 is 0. That's what's going to happen because it can't be connected in that case. But that's equal to 0 over n plus 1, which equals to I over n plus 1. Which is the same situation here. And so, in all possible cases, what we have is the probability being connected given I of the y sub j's equal to 0 is I over n plus 1. Okay? So, when r is equal to n plus 1, then the probability that we have a connected graph, which was equal to this sum, as I runs from 0 to n plus 1, the probability of connected, given I of y sub j is equal to 0, and then this is times, I have to write it down here. Remember, it was n plus 1, choose I, k over n plus 1 plus k, raised to the I, and here it was n plus 1 over n plus 1 plus k, raised to the n plus 1 minus I. That's equal to a sum as I runs from 0 to n plus 1. Okay, so we have an answer for this. It was I over n plus 1. And then times this n plus 1, choose I, k to the n, k over n plus 1 plus k raised to the I times n plus 1 over n plus 1 plus k raised to n plus 1 minus I. Here we'll take out the n plus 1 outside the sum. And this is the sum as I runs from 1 to n plus 1. I'm sorry, 0. Then n plus, well, it's an I. And then n plus 1 choose I. K over n plus 1 plus k. I. N plus 1 over n plus 1 plus k raised to the n plus 1 minus I. Now look, this here's the PDF of a binomial with n plus 1 trials. Okay, that's what this is. And you're multiplying it by I. So this is the probability right here, the PDF, the PMF, I should say, for a binomial that you have I successes. And you're multiplying it by I. And so what that does is that gives you the expected value of that binomial. This is equal to 1 over n plus 1 times the expected value of a binomial random variable. Random variable with n plus 1 trials and p equal to, it was k over n plus 1 plus k. So that's equal to 1 over n plus 1. Remember, we multiply by the number of times we did this, which is n plus 1, the number of trials, and times the chance of success, which is k over n plus 1 plus k, which is equal to k over n plus 1 plus k. And that's what we're supposed to get, okay, for the probability of connectedness. In the n plus 1 case, r equals n plus 1. All right. Thus, so I'll say this. So the statement is true. That's the limit. For n or r equal to n plus 1. Thus, by strong induction, the limit is true. Okay, that ends the proof of the lemma. Okay. So remember, we're getting close to being done for the lecture. But remember, our question was the probability. So we're going back to our question. Probability that the random graph is connected. Okay, that's what we were talking about. That was equal to a sum as k runs from 1 to n of p of the graph being connected, probability of the graph being connected, given that n was equal to k, times the probability of that n is equal to k. And then here, this is, let me remind you, what was n? N is the first, k, such that x of k of I, x superscript, base of I, it was I naught, is one of the previous. x sub m, x raised to m, of I naught with m being 0 up to k minus 1. All right. Okay. Now, this part here is going to be equal to, by our limit, the sum. So what we value by the limit is this part. Okay. It's the sum as k runs from 1 to n of k over n, p, the probability that n equals to k. Okay. So that's by the lemma. Our work by the lemma, where in our lemma where R in the lemma is n minus k. So what we have is the probability of the connected graph is equal to, okay, so it would be 1 over n, we'll take out that n, sum as k runs from 1 to n of k times the probability that n is equal to k. And what this is 1 over n times the expected value of n. Okay, so we need to compute the expected value of n. So the way we're going to do this is with the indicator function. So that's right, we're not done. Now to compute expected value of n, we define I sub j, or I sub I is what I call it. It's equal to 1 if I is less than or equal to n, and it's equal to 0 if I is bigger than n. Hence, when we talk about n, it's nothing more than the sum as I runs from 1 to infinity of I sub I. Okay. So, the expected value then, what I'm working about, it's equal to the expected value of the sum as I runs from 1 to infinity of the I sub i's, and of course we can bring the expected value inside the sum. So this is the sum as I runs from 1 to infinity of the expected value of i's, which is equal to the sum as I runs from 1 to infinity that n is greater than or equal to I. We've done that type of work before. Okay, now, the probability that n is greater than or equal to I. That's equal to the probability that x of I naught, x squared I naught, including I naught. Here, let me just write it out this way. All the way up to x of I minus 1. All these are all distinct. This is I naught. Okay, that's what that's equal to. And so this is equal to the probability that x of I naught is equal to some j sub 1 with j sub 1 being different than I sub naught. X of j sub 1 is equal to some j sub 2 with two things. J sub 2 is different than j sub 1 and j sub 2 is different than I sub naught. All the way, keep going, all the way up to x of j sub I minus 2 is equal to j sub I minus 1 with j sub I minus 1 being different than j sub I minus 2 being different. And j sub I minus 1 is different than j sub I minus 3. Different, okay? And all the way up down to j sub I minus 1 being different than I sub naught. Okay? That's what we have. It's hard to read, but that's what it says. Follow that. Now, due to the independence of this x, how it acts, where it sends something is independent where it sends something else. Okay? We can break this probability of this intersection into the product of these probabilities. So this is equal to the probability that x of I naught is is equal to j sub 1 with j sub 1 being different than I naught times the probability that x of j1 is equal to j sub 2 with j2 being different than j1 and j2 being different than I naught times, okay, all the way up to the probability that x of j sub I minus 2 is equal to j sub I minus 1, where j sub I minus 1 is different than j sub I minus 2, okay, and so forth all the way down to j sub I minus 1 is different than I sub naught. All right, so let's look at each one of these probabilities. Okay, so what's the chance that x of I naught was sent to something besides itself, where we have n nodes? And so the chance of that happening is n minus 1 over n, because everything's equally likely to happen. Now, what's the chance that j sub 1 is sent to something that isn't j sub 1 or j sub 0? That's n minus 2 over n times. We're going to keep going. And so what is this here? It's going to be, lastly, it's going to be n minus I plus 1 over n. It's going to be the last. you can think of it this way, really, what we're subtracting from n is the indice that we're getting out. So here it's I minus 1, so it's minus I plus 1. That's a quick way of seeing the pattern of why this is the ending probability. Okay, so how can we rewrite that? That's the same thing as n minus 1 factorial over, well that isn't quite n minus 1 factorial, but it's over n minus I factorial. And then we have n, how many terms do we have here? We have to the I minus 1 term. So that's what that is. Here we go. We're almost done. As the rock would say, finally, we have the probability that the graph is connected. It's equal to, we know it's 1 over n times the expected value n. What we're doing is computing the expected value n. So we're just going to write this up in a nice way. Well, that's equal to 1 over n times the sum as I run from 1 to infinity of, here, really this should be I run from 1 to n. Okay? That's what it's going to be. Because the chance of getting beyond infinity, so the chance of getting beyond n, when we don't have n nodes, is going to be 0. So here, probability that n is greater than or equal to I, that's equal to I running from 1 to n of n minus 1 factorial over n minus I factorial times n, I need a 1 over n out front. Okay, got that? This is what our work that we produced just a few seconds ago is. So this is I minus 1. This is equal to, okay, so I'm going to factor out, pull out the n minus 1 factorial, because that doesn't depend on I. I'm going to stick the n in the bottom there, and we'll get as I run from 1 to n, and then I'm going to have 1 over n minus I factorial n to the I. Okay. Okay. Now, that is the correct answer, but I'm going to put it in the same form as our text does. And so what I'm going to tell you is that that's equal to, well, it's n minus 1 factorial, we're just holding on to. And if we write this down, this is going to be expanded. What I mean by writing it down. This is 1 over n minus 1 factorial, and then this just would be n. Plus, this is 1 over n minus 2 factorial, and then this would be n squared. Plus, we keep going. And we eventually get to 1 over, it would be 1 factorial times n to the n minus 1. And then we'd have the last term being 1 over, it would be 0 factorial, and then n to the n. We'll make that a little shorter here so we can see it. So we keep going in this pattern, plus we get to 1 over 1 factorial n to the n minus 1, and then plus the last term is 1 over 0 factorial n to the n. Okay, we can see that. Yes. All right. So that's equal to n minus 1 factorial. And then what I'll do is we'll factor out an n to the n from each one of these terms. And so what I'll get is 1 over n minus 1 factorial. And when I take out n to the n, I need to have n to the n minus 1 here. And then plus, here it's n to the n minus 2 over n minus 2 factorial. And then plus, we'll keep going. Here this is going to be n to the 2. I'm sorry, it's going to be n to the first, right, over 1 factorial, over 1 factorial. And then finally we have n to the, when I pull out n to the n, we'll just have, in the bottom, we just have 1 over 0 factorial. If we think about writing this in reverse order, there's only finitely many of them, what I get is the final answer of n minus 1, this is the answer, over, sorry, let me write it over here. This is n minus 1 factorial over n to the n. And rewriting this, which will be a sum, if you will, as j runs from 0. So I'm starting from the furthest one. And then it's looks like runs to n minus 1 of n to the j all over j factorial. And that's the way our text leaves the answer. Ladies and gentlemen, that's all I want to say at this point about a random graph. That constitutes all of lecture 25 and most of lecture 26. Okay? So we'll try to make up a little bit more time maybe the next time that we go and get through maybe next time 27. Thank you very much.